These are the notes for chapter 20 from McGraw-Hill, and be the first day, starting with 20-1. This is electrochemistry, very related to the last chapter. Back in the last chapter we talked about electrochemistry, and we learned that reduction is gaining of electrons, oxidation is loss of electrons. Remember that, way we remember that, Leo the lion goes grr. Leo, lose electrons, oxidized, LEO. Grr, gain electrons, reduced. Very important to remember that. That's something everybody can remember because it's an easy way to remember it. There are two types of electrochemical processes that we're going to talk about. One of them is voltaic process. And the easy way to remember that is that's what it does. It makes volts. So it takes chemical change and produces electricity. That's what our flashlight cells do, or the batteries that we use, the battery we have in our car, makes electricity from a chemical process. The other process is electrolytic, and you could remember that. Of course, it's the other one. It goes the other way. It starts with electro, and that's what it does. It starts with electrons and electricity and makes a chemical change. So it goes the opposite way. And we're going to talk about mostly voltaic processes today, but we are going to spend a little bit of time talking about plating, which is an electrolytic process. So the first thing that we'll discuss, and you're going to see a question on the quiz and the test about this, it'll tell you that you have some metal and you put it in some solution. It says, will there be plating? What type of plating will occur? So the way you do that, we have this chart that we've had on our possibly useful page most of the year, and you probably haven't used it a lot since chapter 7, but it's basically an activity series chart. It tells you what's most oxidized, and for single replacement reactions, the way we address that is we said it tells you what is stronger. And that's not really the best term for it, but it's the easiest one to understand. So the higher it is on that chart, the more likely it is to oxidize. If it's higher than another metal, the high metal oxidizes, the low one reduces. And that's very important to remember. So you should make a flashcard about that. These concepts everybody can get, everybody can remember. It's a matter of what time you put in to make sure that you understand these important concepts. So how do we do this? Well, it's a single replacement reaction. So what we are doing is we are, for instance, let's say that we have a copper strip. So here's the copper strip, and it's dipped into iron 2 sulfate, which is FeSO4. Okay? Will it plate? What kind of plating? Well, so write a single replacement. Copper plus FeSO4. Easy enough to do. And what does it produce? Well, we draw a line before the second capital letter on the compound, and we know we're doing a single replacement. We look at the chart. It's on your possibly useful page on the back of the periodic table, and it's the long chart on the side. You look and you find out, iron is above copper of both types, copper 1 and copper 2. So in this case, iron already has the sulfate. It's the strongest, so no reaction, no plating. If it were the other way, if it were iron dipped into copper sulfate, then the iron would kick the copper out, and when it kicks it out, it would plate onto the iron plate. So we would have copper colors start to appear on the iron plate, and there would be copper plating. So that's how you figure out, will it be plated and what kind of plating will occur. And you're going to have at least one question on the quiz and one or two on the test that way. So make sure that you go through that concept enough times till you figure it out. It's not rocket science. Everybody can do that. You just have to put the time in order to go through it enough times to learn it. Alrighty, so we move on. Now we are actually going to get to the voltaic cell, which is what we're going to spend most of the rest of the day on. And voltaic cells are the ones that make volts. So the quiz, you're going to have about a 20-point question on the quiz, and maybe 25 points if that's the only diagram you're drawing. And on the test, you're going to have a voltaic cell to draw that's about 15 to 18 point question. What do you have to be able to do? I'm going to give you two metals, and you draw a voltaic cell from there. Now, there are two general models for a voltaic cell. One of them, like the first one in your notes, has two separate dishes, and it has a bridge that connects it. Now, the main requirements here that you're always on a voltaic cell going to have two separate cells, two half cells. One of them will do oxidation, one will do reduction. The metal that you have in that cell determines what solution that you'll put the metal in. In other words, in this case, we've got copper, so I'm going to say let's put it in copper sulfate. Well, that means that over on the zinc side, you need to use zinc sulfate because the solution needs to be the same ending, same last name on both of them. So zinc sulfate, copper sulfate. You could use nitrate, copper 2 nitrate, zinc nitrate. So just make sure that you do your crisscross and write the formula correctly. So that the ending of that, it's just one of your polyatomic ions. It doesn't really matter. I would use sulfate or nitrate for all of them. Just make sure that they both have the same thing. Likewise, if you use a salt bridge, and the salt bridge is the way that we complete the circuit on this electron flow. The electrons go from the loss, they lose in the oxidized, remember Leo, lose electrons oxidized, and they're gained on the other side. That's what a cell is, and batteries work on that principle, that we're basically just moving electrons from one place to another. Moving electrons, that's electricity. So here's a diagram that has the salt bridge. The salt bridge completes the cycle, and basically the thing that you need to make sure in the salt bridge is that the salt that you have in there has the same last name as your two solutions. In this case, sulfate. So we're going to use sodium sulfate. You want to use potassium sulfate? The first part of that doesn't matter. It's just like a spectator. Okay? So we've got, in this diagram, we've got a sodium sulfate salt bridge. So how do we figure out how all this works? Well, we're going to go through it step by step, but just a general run on this is that you look at the two metals, zinc and copper. Zinc is above copper. The one that's higher is oxidized. The other one's reduced. It's that simple. So you find the two metals, the one higher, write oxidized next to it. And the other one, you write reduced. Okay, well, if it's losing electrons, now we know which way the whole cycle's going here. So if it's losing electrons here, then it's going to gain over there. And the sulfate is how we complete the cycle with the charges. The negative to negative sulfate goes through the salt bridge this way, and then the electrons go around, sulfate over, electrons around. So we're basically keeping the whole thing neutral by moving our charges. Now, the salt bridge has sodium sulfate in it. The sodium is going to go this way, while the sulfates go the other way. So that kind of maintains our neutrality. But that gives you an idea how all that goes through. So we're going to go through step by step and draw the voltaic cell. We're going to use all the steps, and if you'll learn the steps, it's very easy to do. Morning. First step, take the two metals and look at the activity series chart that you have, reduction potential chart. Remember, this is a reduction potential chart, and we always have the most oxidized items on top. Doesn't matter whether it's a reduction chart, oxidation chart, they keep it consistent so it's easy for you to use. Well, if the items on top are most oxidized, then obviously they're going to have a negative reduction number. In other words, that tells you that they're not very likely to reduce. The items on the bottom are most likely to reduce, least likely to oxidize. They have a very positive number for reduction. And that's where the numbers come from. Okay, so first step, look at the two metals, zinc, copper. Zinc, that is oxidized, so it's going to lose electrons. So we are going to draw, now we're going to use the other model, and I'm going to advance forward to that on the the notes, it's a couple screens forward. We're going to use zinc on 1 cup, and we're going to put copper Cu out in the big dish. And this model, we're going to advance forward a couple of slides to look at that. This is the voltaic cell with the porous cup. It's the one that we're going to do in the lab, and we're actually going to build this one in the lab. So what this does, instead of having 2 different cups, is it has a large cup, and then there's a porous cup that goes inside. The porous cup does the same thing the salt bridge does. It's porous. It has holes, that small holes that allow the sulfate or the ions to move through the wall and complete the cycle. So we start with the sulfate inside, it goes through the wall to the other solution, electrons go out and around. And that is basically the same as the 2 dish. So the steps are there. If you back up a slide or so, they'll have the steps for how to do this. We've looked at the metals. Zinc is higher, it's oxidized. We write oxidized. Copper is reduced because it's lower. And the oxidized means it loses electrons. So we're going to draw our wire here, and we're going to lose electrons here, and we're going to gain electrons there. So we're going to draw 2 arrows, one of them losing, one gaining, and that helps you know which way the electrons go. And if you want, you could draw a light bulb in here, or we're going to use a multimeter in class. So oxidized means that electrons come from here and go to there. Well, which direction do electrons go? Do they go towards a minus or towards a plus? Opposites attract. So minuses go towards the plus. Minuses are going towards the plus. This has to be the minus pole because that's where the minuses live, right? So they this is the negative electrode. We have a name for that. We call it anode. And the way you can remember that is a negative electrode. A-N-O-D, a negative electrode. We go over here, and the positive has a name too, and that's cathode. And the easy way to remember that is it's got a T that looks a lot like a plus. So the T for the plus, cathode plus. The thing that you can remember to help you with oxidation, anode, reduce, cathode, is that the anode and oxidized always go together. So when we talk about the new cell tomorrow, it's going to be still anode oxidized together. And a way you can remember this, and it's kind of silly, you've heard the old wives' tale about bulls not liking red, like red capes. They don't like anything that you jump into their pen and wave something, they're going to knock your butt off. So it doesn't matter whether it's red. But we'll just think of this, oxes, bulls, kind of same thing. So we're going to say an ox chase a red cat. And that means that anode and oxidized are always paired together. Reduced and cathode are always paired together. On the quiz, I'm going to ask you what kind of reaction happens at the cathode, and you would say reduction because of red cat. And it doesn't matter whether it's electrolytic or voltaic cell, those pairs stay together. So we've got the anode oxidized, electrons going away to the reduced cathode, which is positive, and now we need to write solutions. Well, in the copper side, we're going to label this copper 2 sulfate, CuSO4. Over here in the zinc, inside this container, we'll do kind of a cutaway there, that's going to be zinc sulfate. Same ending. Remember, we don't need a salt bridge because we've got a porous cup here. This is the easiest one to draw. Now, we've pretty much got everything done, except we need to write the half reactions. So on the zinc side, we're oxidizing. How do we write a reaction for zinc oxidizing? Well, zinc loses 2 electrons. How do we know it loses 2? You look on the chart, Roman numeral 2, 2b. Okay, Roman numerals 1, 2, or 3 are always their charge. So zinc is going to become zinc 2 plus. How does it do that? By losing 2 electrons. There you go, oxidized. Reduction reaction is gaining. Copper, we'll say copper 2 is copper 2 plus 2E minus yields Cu. There's your reduction reaction. So we've pretty much done everything we need here. The last step is to calculate the voltage. And we use the numbers on your reduction potential chart. How do we do that? Look up the numbers of the two metals, and the E0, the potential of the cell, that says what a cell can make in volts, is its potential voltage, is the E value of the reduced minus the E of the oxidized. In this case, the reduced is copper. Look on your chart, find the value, it's 0.34, positive 0.34, and the oxidized is the zinc. So it's going to be 0.34 minus a minus 0.76 volts. When we add those together, we get 1.10 volts, and that would be the potential. So those are the things that you will be doing on your quiz and your test. They're not anything that, again, is rocket science. If you repeat this or go through the steps, draw enough of these, everybody can do it. It's a matter of whether you decide you want to. So we've looked at those voltaic cells. The steps are there on the notes. We're going to talk about the standard notation for a voltaic cell. And standard notation is basically the oxidized on the left and the reduced on the right. We take out the electrons because it's plus 2e here, and we're losing 2 electrons here. So we just cross through those. And then we just put, instead of an arrow between what's left, we put a single line. So for the zinc, it's going to be Zn solid with a line, converts to Zn2 plus, that's the oxidized side, a double line, which means the porous cup or the salt bridge, and then the other half cell would be Cu2 plus, converts to Cu, because it's gaining 2 electrons. So it's basically these two half reactions with the oxidized on the left, reduced on the right. We get rid of the electrons and use lines instead of arrows and pluses. We've already calculated voltaic cell potentials, so if you need to rerun through that, just rewind a little bit and you can get to that. Finally, we're going to finish up talking about how cell potentials are established. That would be, how does somebody make this chart that you have in your hand? Well, the way we do that is we have a 0 cell, which is called our standard hydrogen cell. And if you look on your chart, the very center of the values, you'll see H is equal to 0.000. Well, just like a ruler has a 0 end, that's our 0 point. Now, we have pluses and minuses, so we measure both ways, but we have to have a reference point. We pick something in the middle, the hydrogen electrode with platinum black wire or electrode. It's a 1 molar hydrogen solution. Could be HCl, 1 molar. That is what we use. How do we determine each metal? Well, we just hook each metal up on the other side through a multimeter, and we read the value. The value goes on the chart. That's how we get those values on the chart. They do them experimentally, and they've done them enough times to where they know that those charts are accurate. So that's how the cell potentials are established. That finishes up the notes for the first day. Go through and work what you can on your review from today, and if you missed something or didn't catch something, you can always rewind these. Good luck and work hard. You'll get this stuff. It's pretty easy if you go over it enough time.